So it's 10 past, and hopefully we'll kick this session off now, and we'll start with an absolutely lovely topic called complex numbers. Always comes up, always nice questions on it, and reasonably straightforward too. So it's a nice area where you pick up nice marks. Just a comment that I'm going to ask you, which is a bit strange, but many of you may not know what complex numbers are used for, but they're used in everything that we do. And certainly, I don't think there's anybody listening to me today that hasn't used complex numbers today several times, and probably will use them today, tonight, tomorrow, hundreds of times. And we just take it for granted just how powerful they are. I'll explain where they're used before, but actually it's wonderful that we have such things as complex numbers. They're much more interesting than ordinary numbers. There's a mathematician, an Irish mathematician called Rowan Hamilton, who is very much involved in the use of not only complex numbers in 2 dimensions, but in many. And I'll tell you about Rowan Hamilton later, but without him we'd be sort of a bit lost. But he was so excited by them that he went for a walk one day with his wife around 1800s, and he figured out a new concept in this space, and he stopped having a chat, and he went immediately, he was walking by the canal in Dublin, and he had to scratch the answer of his theorem into the wall in the bridge in Broom Bridge in Dublin. And every year people go to the mark where he marked it, and we celebrate an awful lot as a result. But without complex numbers, your life would be very, very different. And I've no doubt you've used them many times over lunch. So I'll explain why in a minute. So complex numbers, here we start. Let's start with some terminology. A complex number is a number that has 2 parts. It's got a first part, a real part, 5 maybe, and a second part that's real with an imaginary afterwards, 12i. So 5 plus 12i is a complex number. So it's got a first part and a second part. The second part is made up of a real number and an imaginary element. And the general form is a plus bi, and the set is the set of all complex numbers a plus bi, where a and b are elements of the real numbers, and I is the square root of -1. So that's where that is. And I is considered the square root of -1, and I squared is -1. So that's the complex numbers. You can draw a complex number on an Argand diagram. An Argand diagram is like the Cartesian system. It's like your x and y. It's 2 dimensions. It's on paper. It's vertical and horizontal. But we call this the real, and this is the imaginary axis. So that's how we do it. And this is the number 7 plus I, 12 plus 5i, 3 plus 4i, etc. But it's the full Cartesian system, so it's no different to anything else. It's got the full cohort there. So we can say that's so many out and so many up. It's called the Argand diagram. And this is 2 plus 2i, 4 plus 2i, -1 minus I. So it's in all of the 4 quadrants. And it says here that every complex number is fully defined by 2 coefficients. If 2 complex numbers are equal, they're separate, and real imaginary coefficients are also equal. That's a bit philosophical for the moment, but we'll come back to it in a minute. But we just stop for a minute about complex numbers. What are they? They're just pairs of numbers together. It's like apples and oranges. It's like John has 3 apples and 4 oranges, and Mary has 2 apples and 1 orange. You know, what do they have between them? You just count the apples separately and you count the oranges separately. So it's just a situation where you've got 2 numbers, apples and oranges, or whatever, cans of Coke and crisps or whatever. It doesn't matter. But they're just 2 things in that way. And we catch them separately. And what they're saying here is that if this person here, let's say Darren, has 4 apples and 2 oranges, has the same as somebody else, they have to have 4 apples and 2 oranges. They can't have more apples and compensate with fewer oranges, or vice versa. So both numbers have to be equal. So the real parts have to be equal and the imaginary parts have to be equal. So for example, if a plus bi is c plus di, in other words, 2 numbers, a real and b imaginary, c real and d imaginary, if they're really equal, and if they have exactly the same numbers, then A must be equal to C and B must be equal to D. So they must have the same number of apples and the same number of oranges, or the same number of reals and the same number of imaginaries. It's a 90 degree, so it's the same. They don't overlap. They're seen as perpendicular. The Argand diagram can also be drawn like this, as a distance from 0 plus 0i. So if we look at the point 7 plus I here, we say that's 7 out, real, and 1 imaginary up. That's 12 out and 5 imaginary up. So that's the Argand diagram as almost like a direction from 0 plus 0i. And this number is seen as a bigger number than this number, because it would take longer to walk that distance than it would to do this distance. So it's further away. It's got a bigger length or a bigger modulus, so it's seen as a bigger value. Just as if we were looking at real numbers, in a real number situation, we would say, well, you know, let's look at the real number line, which is not anything near as interesting. But if this is the number line, sort of 4, 6, 8, 10, 8 is bigger than 4. It's twice as big, 4 times as big as 2. And we just multiply, but it's sort of boring. That number line is just up and down, not going anywhere. Okay, you might walk along and, you know, 3 is there and pi might be there and e might be there, but the square root of 2 might be somewhere, but it's really quite boring. Whereas with the complex numbers, you can end up anywhere on the page. So we'll come back to that in a minute. Now, so there's the Argand diagram, and 12 plus 5i is seen as bigger than this because it's a longer stretch. Just as in the numbers, the number 8 is further away from 6, so it's further away. So 8 is bigger than 6, 12 plus 5i is bigger in a way than 7 plus I. For the general complex number z is equal to a plus bi, the modulus, called the absolute value, that means the distance from, of a complex number, represents its distance from the origin. 0 plus 0i. So the modulus or absolute value is represented by vertical bars. So it's really important in complex numbers and in maths in general that we learn off these tricks or these symbols that are really key to us being able to do the questions. So the modulus is the positive value, or the daraibh luach, though I should have thought again of course it's Gaeilge. Daraibh luach, it always is a positive value. So for example, the absolute value of minus 3 is 3. So if you were here on, say, if that was 2 and that's 4, and that's minus 2 and minus 4, this point here, minus 4, is as far away from the origin as 4 is. So that's 4 and that's 4. It would take 4 steps to get there, 4 steps to get there. So that's the absolute value. Just as we can do that with other things as well. So the modulus is given by a plus bi with bars around it. And the value of the modulus is given by z is equal to a squared plus b squared square rooted. Now we'll see how familiar that is just in a minute. So calculate the modulus or absolute value of a complex number 3 plus I. So to do that, you put bars around it, vertical bars, and you get a squared plus b squared for a general case, but this is not a plus bi, it's 3 plus I. So it's 3 squared plus 1 squared. It's not I squared because I is just the direction. 1 is the number of how far you're going to go. So it's 3 squared plus 1 squared. So that's the square root of 10. As the modulus or absolute value represents the distance of the complex number, its value is always positive. So let's look at it here. This is 3 out and 1 up. 3 out and 1 up, 3, 1. But this is a 90 degree. It's like Pythagoras, really. It's exactly the same as if this was x and y. I know it's not. It's called real and imaginary, but it's exactly the same. So what we're looking at here is, we know that this length here is the square of the other 2 lengths from Pythagoras. So 3 squared plus 1 squared is 10 squared, or square root of 10 squared. 3, that will give 10. So this is the square root of 3 squared plus 1 squared. Pythagoras. Exactly the same. So when we see that as a squared plus b squared, it's really something that we don't really have to learn off, because we've already seen it for x squared plus y squared. We've seen it before in Pythagoras. So the Argand diagram there is that that's 12 plus 5i, and that's 7 plus I. And z1 and z2. So is z1 greater than z2? Well, the modulus suggests that it is, because it extends further. If you were to draw a compass and take this as your radius and draw a circle, you'd see that this is well inside it. Equally, if you drew the circle around this, this would be well outside it. So this is bigger, okay? To work out the actual length, we would say 12 and 5. 12 squared plus 5 squared, square rooted. That's 169, and that turns out to be 13. Whereas this one is just 7 and 1. 7 squared plus 1 squared is the square root of 50. And the square root of 50 is about 7 and a bit, not much more, whereas that's 13. And 13 is bigger than, in terms of the Darab-Luach, or the absolute value, Z2 is bigger than Z1 because it's further from 0, 0. And that's that topic. Just to remind you, when you're looking at the resources online on maths.griffith.ie, you'll see that we've broken the topics into subtopics. So for complex numbers, this bit now deals with polar representation. So what we're doing here is it's a small topic. If this is a gap you want to fill or something, or you want to look back on that, you say, oh, that's the bit I want to look at again, or whatever. And it also allows you to look at all the bits that you know and just skip all those. Say, don't need to look at that, don't need to look at that, happy with that, put it away. So it's just really a sort of a guide into the bits you might want to look over. So polar representation. Here we've got the same complex number again. We've got 4 plus 3i. So it's 4 out and 3 up. But if we look at it, we know that that's a 90-degree angle. This is the imaginary component, and this is the real component. And we know that the modulus is 4 squared plus 3 squared is 5, or the square root of 25 is 5. But is there another way of doing it? Well, given that it's a 90-degree, we could consider that as the angle theta as well. Now, if we look at the angle theta, anytime I see a triangle, the first thing I do with an angle theta in a right angle is I draw this arrow. First thing I do, and I say, well, this is the angle opposite this one, so I call that the opposite, because this is the 90-degree. The one facing the 90-degree must be the hypotenuse. So that's the Taobh, that's the Orcorach, Oscailge. And then I look at this one, there's only one left. Sorry, that's incorrect, obviously. That must be the adjacent. I'll fix that note. That obviously is adjacent, apologies. Okay, so opposite, adjacent, and hypotenuse. Okay, so that's what we have there on that. So let's look at then if that's the case. If that is the case, what is the tan of the various angles? Well, the tan is the opposite over adjacent, or Orcorach, or Conjugate, and then the sine is the opposite over the hypotenuse, and the cosine is the adjacent over the hypotenuse. So tan is really 3 over 4. Sine is 3 over 5, and cosine is 4 over 5. So now, here is my original u is equal to 4 plus 3i. I'm now going to multiply this by 5 over 5. So 5 over 5, 5 because 5 is the actual length. So 5 into 4 plus 3i over 5. So that's 5 into 4 over 5 plus 3 over 5 times I. So u is equal to 4 over 5 plus I, 3 over 5. But what is 4 over 5? 4 over 5 is cosine theta, and I is sine theta. So what I've done is we've managed to change this into u is equal to 5 which is the modulus times cosine theta plus I sine theta, the standard form of the polar representation. So u is equal to 5 into cosine theta plus I sine theta. And that's the way we can now describe that. So that's for your standard phi one. But if we were to do it for your standard a plus bi one, there's your b and your a. There's your tan. Tan is b over a. So if tan of theta is b over a, theta must be inverse tan of b over a, the angle that has a tan of b over a. So that's how we get our theta. And then we can say theta is that. There's our imaginary and our real. There's our angles there. And we can say x plus bi, put the r in front and divide by r. A over r, b over r, bring them all together. And we get the standard form of an equation in polar is that z, the complex number, is r, the distance from naught plus naught I times cosine theta plus I sine theta. And that's it there. So that's the way we describe a complex number in polar notation. Z is equal to r cosine theta plus I sine theta. And that's the polar representation of complex numbers. This section on the addition and subtraction and multiplication, but certainly the addition and subtraction of complex numbers, probably couldn't be easier. Really, it's great that they give us marks for doing this, but really it couldn't be more straightforward. Just imagine the complex numbers as apples and oranges. So if somebody has 3 apples and 4 oranges, and somebody else has 2 apples and 2 oranges, can you add them up together? And that's all that's happening here. Or if somebody has lots of apples and lots of oranges, and somebody borrows some of them, how many are left? So it's really just 2 additions and 2 subtractions going together. So let's look at complex numbers. If u is a complex number 1 plus 3i, and v is the complex number 4 plus 2i, find u plus v. Add the 2 up. So an apple and 3 oranges, 4 apples and 2 oranges, what do they add to? So what we do is we join the 2 up together. So we write the whole thing out. U plus v is 1 plus 3i plus 4 plus 2i. Now I group them together. I group the real ones together, the 1 and the 4. Let's call those the apples for the moment, and the imaginaries, the oranges. So I've got 1 plus 3i, 4 plus 2i. Regrouping them, I can see that the 1 and the 4 are the real parts, and the 3i and the 2i are the imaginary parts. So I get 1 plus 4 is 5, 3i plus 2i is 5i. Alternatively, I could have done it here. 1 plus 3i, 4 plus 2i over 5 plus 5i. So that's how it's done. I could have done this visually as well, starting at 0, 0, 0 plus 1i. I could go out 1 plus 3i, so 1 out and 3 up, almost like east and north. And then I go out 4 from there and 2 up. So I get 1 plus 3i, 4 plus 2i gives me to there. Or I could have started with 4 plus 2i and then 1 plus 3i. So the representation, I can do it that way. So it doesn't matter whether I add u plus v or v plus u, I end up in the same place. 1 plus 3i, 4 plus 2i, 5 plus 5i. It gets the same answer whether I put 1 on top or 1 on the bottom. It doesn't matter. Addition is commutative, okay? Now we look at subtraction. Somebody brought in 5 apples and 5 oranges, and somebody wanted to borrow or eat 1 apple and 3 oranges. How many are left? So we've got Z1 here, a complex number in the Argand diagram, and another one. We want to take one from the other. So if Z1 is 5 plus 5i, and Z2 is this, take it, subtract this from this. So Z1 minus Z2 is 5 plus 5i minus, with a bracket around, 1 plus 3i. So 5 plus 5i minus 1 minus 3i, multiplying in by the minus. Again, I group them together. There's 5 and the minus 1 here. and there's 5i and minus 3i on the imaginaries there. So that gives me 5 minus 1 is 4, 5i minus 3i is 2i. I could have done it here as well, just line them up, put the real ones together, 5 and minus 1, and do the imaginaries together, and I get that. So 4 plus 2i. So for example, if I started off way up here at 5 plus 5i, and I took 1 plus 3i from it, I'd end up here. If I took 4 plus 2i from it, I'd end up here, and then the remainder to get back, the 1 plus 3i. So I could take the 1 plus 3i and then the other 4 plus 2i, or the 4 plus 2i and the 1 plus 3i. So it just shows you the mechanisms. That's my u, that's my v, that's u plus v, so I'm subtracting as I go along. Now, the analogy of the apples and the oranges stop at this stage, because we're now talking about multiplication. Multiplication is the next thing we can do with complex numbers, and it's really interesting. It's actually one of the reasons why you use complex numbers all the time. But I'm going to multiply two numbers, 1 plus I by 3 plus I. Both are complex numbers. Now, the Americans do this. American high school students, they use what they call the FOIL method or whatever for multiplication, 1 plus I, 3 plus I, and they call it first, outside, inside, last. So let's multiply these two pairs together. So the first one is the first and the first, so that's 3. First by the last is I. I'll keep going. Then I've got the middle ones, insides, I by 3, and then the last I by I squared. So I end up with 3 plus I3 plus I squared. I squared is tricky, but I squared is defined as minus 1. So I'm going to change that now to 3 plus I3 minus 1. So let's see how I do it here. I multiplied in 1 by 3 plus I times 3 plus I, and I worked it all out. And I ended up here changing that I squared for the minus 1. Now grouping them together, the 3 and the minus 1 gives me 2, and the I plus 3i gives me 4i imaginary. So what this is saying is that on an Argand diagram, if I multiply 1 plus I by 3 plus I get this here. And it's fine. I mean, I don't doubt it. I'm sure it's true. It's all very good and all that. But it's sort of a bit random, really, you know, in that we're used to doing multiplication in numbers, and we're used to saying if we've got the number line that say the number 2 by the number 3, 2 by 3 is 2 by 3 is 6. So if we take this 2 here and do it 3 times, so 2 and 2 and 2 gives me to 6. Or if we take 3 and do it twice, we end up here. We sort of understand that. But the notion that this thing here multiplied by this gives us this, that Z1, Z2, Z3 is a bit still strange. Like, why would a number here multiplied by a number there give us a number there? Why would Z1 by Z2 give us Z3? Hard to know, but for the moment, let's assume it does. This is correct, but maybe it's not intuitive. It's just an answer. So yeah, put it down. It's fine. But I don't really understand it as clearly as I do with the real numbers. I can understand this when I can get a sense of that, get a sense of what's going on there. Okay. There's the multiplication representation again. This number by this number gives us this number. But there's a bit of a hint. Basically, that number there, the first one, has a theta 1. This number here is a theta 2. And the answer here has a theta 3. And maybe there's a connection between those theta 1s, theta 2s, and theta 3s. Okay? It's like as if there might be some link between them. Okay. The next thing we're looking at is we're looking at complex numbers, and it's very difficult to divide complex numbers. So before we do that, we have to actually bring in a means of getting around it. So what we do is we bring in a sort of a catalyst in a way, something that we introduce, it does its job, and then it comes back out of the equation. So we want to bring in a means of actually finding out the division. It's not straightforward to do complex number division without a sort of a trick. So we're going to take a turn now. We're going to look at a thing called a complex conjugate. Okay. So where a complex number is denoted by z equals a plus bi, the complex, that's a complex Conjugate we're talking about there, Australian. The complex conjugate is denoted by z bar is a plus bi bar. So you put a bar on the top, a plus bi bar. And z bar is the same as a plus bi, but with the number there of minus rather than plus. And there's a special characteristic about the complex conjugate of a number. When you add two of them together, you add a number to its complex conjugate, you don't have any imaginary bit left. And when you multiply a complex number by its complex conjugate, you don't have any imaginary number left either. So when you add them or multiply them, they yield a real number. Before I move on though, I just want to sort of, it strikes me there with all these letters and bars and stuff like that. It's really important that we get our symbols right and our letters right and our understanding of the symbols. They're just symbols. Like in English, you've learned A, B, all the way to Z, and capital A to capital Z. It's 52 of them. Then you've learned the apostrophes, and you've learned the commas and the full stops, and you've learned the whatever, the colons and whatever, and the exclamation marks. And they all help understand that little bit more about exactly what we mean. We know when to use a capital letter and a full stop and all that sort of stuff. Well, maths is the same. We've learned the 0 to 9, we've learned the plus and the divide and the multiply and all that. We've learned about the sine and the cosine, etc. But there's also a few more. So when they see things like Z bar, that's the complex conjugate. When we see this, that's the modulus. And these symbols, when you don't recognize them, can put you off, but they're no more difficult than the square root that we've become more familiar with, or the cubic root. They're just a shorthand way of doing it, but it's really important that you recognize the symbols, because there's not much in it once you know, oh, colon, oh, that's fine, or an apostrophe, oh, full stop, yeah, okay, I can put that in, that's no problem. It's not any more difficult than any other letter you've learned, and it's just knowing those symbols. So just don't be put off by this. It's not a foreign alien language that you don't know. It's just a way of saying, oh, it's the same number, but not the same imaginary part. The imaginary part is opposite. So let's look at complex conjugates and their representation. There's a complex number 3 plus 4i. And its twin, or its complex conjugate, is 3 minus 4i. It's basically, for all the words, like a mirror image of itself. That's what it is. It's seeking to say, where is the element of my reflection in this mirror here? So I just look at that and say, there's the reflection. Looking in, and I can see on the other side that that's the actual reflection. So 3 plus 4i, if I look in physics, I could see at the back of the lens or whatever. That's the imaginary image in there, just looking at yourself in a mirror. Equally, it doesn't have to be that one. This point here is a perfectly valid complex number. And when it looks into the mirror, it sees its reflection on the other side. So if this is Z1, this is Z1 bar. If this happens to be Z2, this is Z2 bar. So each has its own complex conjugate. Similarly, it can be on this side or any side. This could be the complex number. This could be Z3 minus 1 minus I. And if it looks, it sees the opposite. It sees its twin, and it says this is Z3 bar. And likewise. So it's exactly the same as a reflection in the real axis. So let's add complex numbers together with their complex conjugate. This is 1 plus 2i and 1 minus 2i. So 1 plus 2i and 1 minus 2i, you 2 i's and minus 2 i's, they would cancel. So you just get 2. That's the answer. So add the 2, you end up with a real number. A real number on the real line, there's no imaginary bit. Now it's still 2 plus 0i, but it's really 2. And if you look at this even in terms of, say, east and west and stuff, or north and south, here we go. 1 plus 2 is go out east 1 and go up 2 north. And the next one is go out east 1 and go down 2 north, or go down 2 south. This would have down north. So go down south, so it's minus. So 1 plus 2 up, 1 plus 2 down, and you end up in the same place. So that's the adding of complex conjugates. So they should always, because they're designed to, become real numbers. Multiplying complex conjugates together. Here we got 1 plus 2i and 1 minus 2i. 1 plus 2i by 1 minus 2i. And the answer here is 5. So that by that is that. Okay, maybe it is. Well, let's see if it is. Do the FOIL method. 1 by 1 is 1. 1 by 2i is minus 2i. That's the outside. Inside is plus 2i. And then 2i by 2i is 4i squared. But then there's a minus. Now the 2i and the minus 2i are cancelling. And that's good news because we don't want them. I squared is really minus 1. So it's 1 plus minus 4 times minus 1. Minus by minus is plus. So that's 1 plus 4. That's 5. Or 5 plus 0i if we were just counting those i's. So again, we see this number here multiplied by this number here gives us this. Interesting. This is the angle here, theta 1. And this would be the same angle, theta 1. Well, really minus theta 1 because of the mirror image. And theta 1 and theta 1, or theta 1 and theta 2, if you wanted to call it that, added together, seem to give us a 0, which is nice. We'll talk about that. Why did we do all this thing with the complex conjugate? It was because we couldn't divide. So we now can divide in complex numbers this way. So if we're asked to do 1 plus 8i over 2 plus 3i, we can't do it. But we bring in the complex conjugate of the thing on the bottom, because it's the bit on the bottom we don't like. We can deal with it on the top, but on the bottom it's a mess. So what we're going to do is we're going to take this expression here and multiply both above and below by 2 minus 3i. So 1 plus 8i by 2 plus minus 3i and 2 plus 3i by 2 minus 3i. That is the same question because they're equal. But let's expand it and see how it works. So 1 plus, so you might try that now for a moment. Just take a minute and decide whether you want to do the line on the top or on the bottom. But just multiply 1 plus 8i by 2 minus 3i. And the other one is 2 plus 3i by 2 minus 3i. So just give that a go for a minute and see how you get on. Okay, FOIL method. So 1 plus 8i by 2 minus 3i. So 1 by 2, and then 1 by 2 first, and then 1 by minus 3, and then the middle 8i by 2, and then 8i by minus 3i. So that's first, outside, inside, last. So 1 by 2 is 2, 1 by minus 3i is minus 3i, 8i by 2 is 16i, and 8 by 3 is 24. I by I is I squared, 8 by plus by minus is minus. So that's the expression. I'm going to tidy up this I squared and make that a minus 1. So that's minus 24 times minus 1. So 2 minus 3i plus 16i plus 24. I'm now going to group the reals together, the 2 and the 24, to give me 26. And 16 minus 3, they're both i's, 13i. So the answer I get for the top line was 26 plus 13i. That was the top line. Okay. Now the bottom line was 2 plus 3i by 2 minus 3i. Again, the FOIL method, 2 by 2, 2 by minus 3i, 3i by 2, 3i by minus 3i, and I expand them out. 2 by 2 is 4, 2 by minus 3i is minus 6i, 3i by 2 is 6i, 3 by 3 is 9, 3 by plus by minus is minus, and I by I is I squared. Okay, so 4 minus 6i plus 6i. I'm going to change that I squared into a minus 1. So it's minus 9 times minus 1. And now I get 4 plus 6i plus, or minus 6i plus 6i plus 9. But luckily, the pluses and the minuses in terms of i's cancel. And that's what we'd expect. The only reason we did this on the bottom was to get rid of the imaginary parts. So if we made a mistake here, we can try it again, or we can say we were expecting something different, but we really have to get, or should be expecting, a real number on the bottom. So 4 plus 9 is 13. We can leave in the not I for a moment and say 13. So the original equation of 1 plus 8i over 2 plus 3i, that's cancelled, is this over 13. 13 into 26 goes 2, and 13 into 13i goes I. So that's the answer. So we've now managed to do division in complex numbers. We took 1 plus 8i, a complex number, divided by another one, and then ended up with another one. So visually, the way that works is that there's 1 plus 8i, there's 2 plus 3i, the number we're dividing by, and that's the answer. So that. 3 numbers on the complex plane that we got it. Again, it's sort of interesting. Yeah, we can believe it, but actually, there was the angle of the first one. There's the angle of the second one, and there's the angle of the third one. And we'll see later there's a direct connection between them. So that's the angle of the first, that's the angle of the second, and that's the angle of the third. So we've done addition, subtraction, multiplication, and division of complex numbers. We've put them in the Argand diagram. We've done the polar representation of them. So we know how to handle complex numbers. Let's look at some of the observations. Why do they come about? Why are they so important? How are they so useful, really? Well, observations on complex numbers. When you multiply complex number Z3 from Z1 times Z2, the angle of the product is given by the sum of the other two angles. So the angle of the third is the sum of the other two angles. And the angles are defined as those made by the origin and the naught plus naught I. So our standard way of doing it. That's an interesting observation. When dividing complex numbers, where Z3 is Z1 over Z2, the angle of the product is given by subtracting the angle of the denominator from the angle of the numerator. So O3 is O1 minus O2. And again, the angles are made by the angles with the naught plus naught and the real axis. When multiplying complex number for Z3 is equal to Z1 by Z2, the modulus, the size, the length, how far it is from naught plus naught I, is given by the product of the other two moduli. So the modulus of Z3, the size of it, the length of it, is the length of the first by the length of the second. And when dividing complex numbers where Z3 is Z1 over Z2, the modulus of the product is given by dividing the modulus of one over the other. So Z3, what you're left with, is the first one divided by the length of the second. And that's reassuring in a way, Because imagine if this wasn't complex numbers, but it was just ordinary numbers. We're used to 2 times 3 being 6. That length times that brings you out to here. So three of the 2's or 2 of the 3's would give us there. So we're used to that. We're used to 2 by 3 equals 6. So the length of the 2 by the length of the 3 is 6. We're also used to the length of the 6 divided by the length of the 3 being 2 in terms of moduluses. And they're complex numbers. Remember that that's 6 plus naught I, 3 plus naught I, 2 plus naught I. It's just saying that it happens for all the other ones as well. So what does that mean visually? It means this. If I take the number 3 plus I here and multiply 1 plus 2I, I get 1 plus 7I. And effectively what happens is, in terms of the angles, the first angle, theta 1, is 18.43. The second angle is this one here, 63. And the third angle is their angle in common, that they added the 2. So if I multiply something by something else, I add the angles. I'm actually rotating the whole thing. I'm rotating the thing nicely by the amount of the angle that I have. So if this is the angle I've had myself, and I multiply by this, I add my own angle back in to bring it up to here. Multiplying is counterclockwise, so I'm always going anti-clockwise, that way for multiplication. And that's the addition. How do you find the angle? Well, you could look at it there by calculating it, but that's not how I did it. Standard way to find an angle is, you have your point, whatever that point is. No idea what this distance here, but I think it's 3 there and 5. And this is whatever that is, I don't know, but we can work it out. It's 3 squared plus 5 squared. If this is the angle theta that I want to find, this will be opposite. This will be hypotenuse. This will be adjacent. Or Conjugate and Theorem will be every time. This is a 90 degree. So tan of theta is 3 over 5. Theta is inverse tan 3 over 5. If I put in 3 over 5 in a calculator, hit the inverse tan, I'll find out what that angle is. And I can do that for any single complex number I want. I could do it for the 3 plus 1, then 1 plus 2, the 1 plus 7. And that's where I got those angles from. Division. Division is interesting too, in that division says that if I start off at 1 plus 7i here and divide by 1 plus 2i, I end up here. So this angle, this angle. So again, I seem to be subtracting angles. So this angle here was quite a lot, 81 degrees. I took away 63 from it, which was quite a lot, and I end up with just 18 left or whatever. But division is a clockwise movement, okay? And it's important too that if you're dividing by something small, well, if you multiply by something big, it gets bigger and bigger and bigger. If you multiply by something less than 1, it gets smaller, smaller, smaller. But effectively what we're finding is that, let's say I take the number 1 and I and minus 1 and minus I. If I multiply something by 1, it stays the same. 1 by 1 by 1 is, 1 by minus 1 flips all right. 1 says the same. If I multiply something by I end up here. If I multiply by I again, I end up here. By I again here, and by I again here. Effectively, I'm just rotating in a circle. If I decide to multiply by something less than 1, I'll end up with something like this repeatedly. Whereas if I were to do the opposite and decide to multiply by something larger than 1, and this, let's say this was just 1 here, what I'd find here is I'd be getting bigger all the time. But multiplying is rotating. Multiplying is rotating. If I was dividing, it would be coming down. If I'm dividing by a big number, I'd be spiraling in or whatever. Now the opposite direction. Okay? But you can see how it happens. So you can see it in games and stuff like that, but really that's not why we use complex numbers. How often do we decide to actually multiply by imaginary numbers? You might think not that often. You know, when did you last multiply by I? When did you decide that you wanted this I here to be up here, apart from your maths? Well, if you think about it, what you're doing there is you're rotating by 90 degrees. And I'm just going to put well, I won't show that now, the back of the camera, but you've often seen a picture in landscape that you want to see in portrait, that you want to see in landscape, that you want to see back in portrait. How many pictures do you do like that, that you actually just need to turn? Every time you do that, you're keeping much the same picture in terms of size. You don't become huge or tiny like the spiral inside out, much the same. You might see more of it in one side or another, but you're multiplying by I, by the imaginary number I. My guess is you did that probably, I don't know how many thousands of times today, but really quite a bit. So I don't know if I'm there somewhere, but see if I can get in there. But I'm sure at some stage I'll actually rotate myself just for the crack. Okay, just in that picture. But all I'm doing is rotating through 90 degrees. Okay, so if I come in here and I say, okay, I think I can rotate here for the fun. Maybe I shouldn't because it might be disorienting, but you get the idea. I'll share the screen again. But that's what you do. So yes, you used complex numbers today, last week, you'll use them tonight, and you'll use them a million times tomorrow. Okay. We now move on to a topic in complex numbers that's really, really clean. It's amazing. It brings a lot of the trigonometry, the triantonic together, and actually the solution of a lot of those cos squareds, sine squareds, formulae, and all that stuff. Complex numbers characteristics. Now, way back in the polar part of this, we also found out that we could describe a complex number not as a plus bi, but z is equal to r cos theta plus I sine theta. But when you think about theta, let's imagine that theta is an angle. Let's say it's 30 degrees or something like that, whatever. But theta is actually the same as theta plus 2 pi or theta plus 360 degrees. Like if you have this angle with, let's say that's the angle theta, whatever that angle is. That's the same angle as this angle with 360 degrees added on. Or maybe, you know, even more than that, twice, one, twice. So it'd be theta plus 720 degrees, or theta plus 4 pi, or theta plus 2 pi. In other words, if you add 2 pi or 4 pi or 6 pi or whatever, you still get the same answer. And that's okay, but that actually turns out to be very helpful when we're finding the roots of something. So basically, theta is theta plus 2 pi, theta plus 4 pi, theta plus 6 pi, or theta plus 360, 720, 1080. So for every complex number, z is equal to r cos theta plus I sine theta. The nth power, and this is what the Moivre figured out, the nth power is given by, well, you just do this to the n and this to the n. So if that's z to the n, this must be r to the n, and this must be this to the n. Nothing finding out on that. But what de Moivre found out was that it's also, this one here is also r to the n cos n theta plus I sine n theta. So cos theta plus I sine theta to the power of n is equal to cos n theta plus I sine n theta. And that's really handy. So that's the Moivre's theorem. It's in that, just that little nugget there. The R to the N is fine. That's the same. That's the Moivre's theorem. Note that every complex number can be expressed as or cos theta plus I sine theta, or adding 2n or 4n or 2 pi or 4 pi or 6 pi or whatever. So the two square roots can be written as follows. The first one is z to the half. If you wanted the half or the square root of something, remember that x is equal to x to the half, the square root. So instead of having z to the n, you want z to the half is r to the half, this divided by 2 and this divided by 2. So that's on its own. And then you try it when pi is 1 or pi is 2 and pi is 3. So you start putting in these answers here. And you start getting two answers for the square root. The nth roots can be written as follows. So you can have the first one where you just have pi equals 1, or sorry, 2n pi. So you have n equal to 1, n equal to 2, n equal to 3, n equal to 4, n equal to 5, all the way down to n equal to n. So if you've got n roots, like fifth roots, then you'd have 5 of them. If there's 10th roots you're looking for, then you'd have 10 of them. If the square roots, you just have 2, cubic roots, you just have 3. And you get them by slipping in this technique here. So what does all this mean? Well, let's look at the square roots of 1. 1 plus 0i is just 1. That's just an ordinary everyday number. And the square root of 1, I think, was either plus or minus 1. So it's either 1 or minus 1. And there's only 2 of them because they're square roots. And they're funny 180 degrees apart. Probably didn't think about it like that before. Never sort of looked at it like that. We said, oh, it's just plus or minus 1. But actually, in terms of complex numbers, this is one of them and that's the other of them. And they're sort of 180 degrees apart. Or 2n pi, like 2 pi would be 2n pi. And if we're halving that, it'd be just, n would be half of that, so it'd be just pi. 2 times a half by pi. So pi 180. What are the square roots of plus or minus 1? There we see it. We see them there. The square roots are at this and at this, plus or minus 1. How do we get the fourth roots of 1? Fourth roots. Okay. Well, the fourth root is the square root of the square root. So the fourth root of 1 will be the square root of 1. So the square root of 1, though, we know, I think, should be plus or minus 1. So we should have the square root of 1s, or we should have the square root of minus 1s. But the answers, if there's 4 roots, really, we should be looking at 90 degrees apart, because it's 360 divided by 4, which is 90 degrees, whereas with the square roots, we had 360 divided by 2. And if you look at it, 1 by 1 by 1 by 1 is 1. Minus 1 by minus 1 by minus 1 by minus 1 is 1. But I by I by I by I is minus 1. By I is minus 1. And minus 1 by minus 1 is 1. So I to the 4 is 1. And similarly, minus I to the 4 is 1. And this is what do we call that? Minus 1 to the 4. And this is 1 to the 4. If we were to imagine these as rotations for a moment, and let's say I is just a 90-degree rotation. Let's do that 4 times. 1, 2, 3, 4. I'm back here at 1. So the something by itself 4 times ends up here is a root, a fourth root. So I, fourth root, I to the 4 is 1. Or the fourth root of 1 is certainly I is one answer. What about the minus 1? Let's do that 4 times. So once, twice, 3 times, 4 times. Minus 1 times is 1. that does it as well. So the square root of, sorry, the fourth root of 1 happens to be -1 as well. What about this one here? Well, 3/4 way around, that's 3, that's 1, and then 1, 2, 3/4 way around, and then 1, 2, 3/4 way around, and then 1, 2, 3, 3/4 way around. So even with that, 270 degrees by 4 brings us all the way around back here. Okay? Or that might be, what is it? That's pi, that's 3 pi over 2, is it? By 4. So that'll be 6 pi, 3 times around. It's the same again. So they're the 4 roots of that. So that's how we would do that. So what we do is we find one root, and then we say there's 360 degrees divided by 4. The others must be 90 degrees apart. There's the fourth root of that. The fourth root, I've got all the answers. The fourth root of that is the square root of plus or minus. So that's the square root of 1 or the square root of minus. The square root of 1 is plus or minus. The square root of -1 is plus or minus I. Because I by I is -1 and minus I by minus I is -1. So there's the 4 roots. So it's neat. And again, we can see the loop on that. There they are, 1, 2, 3, and 4. Cubic roots of 1 plus 0i. How do we do this? Well, it's 360 degrees, and there's 3 of them. So whenever we get one of them, the other should be 120 degrees apart, or whatever that is in terms of pi, right? It's, what is it, 2 pi over 3 or whatever. So there's 1. 1 is certainly the cubic root of 1 is certainly 1, because 1 by 1 by 1 is certainly 1. But what about this one here? Third of the way out, third of the way out, and third of the way back. Well, if we went out 120 degrees, and then again, we'd end up here. So something by itself 3 times, a turn minus 0.05 plus root 3 over 2i. This is this number here. It is a complex number. It has an angle of 120. And we know that if we multiply that by itself 3 times, we get 120, 240, and 360, so we're back. And we also know that the modulus of this is actually 1, because I think it's this amount by this amount. So this is root 3 over 2, and that's a half. So this turns out to be, that's root 3 over 2. So that's the I part, and that's the minus part. So a half squared plus that squared. Well, let's work out the modulus for the moment. It's a 90 degree. So what is the actual Pythagoras height of that? So it's a half squared plus root 3 over 2 squared. I'm not going to worry about the I, because it's a distance, remember. I'm talking about distance, so it's like a squared plus b squared. We forgot about the I. So a half over that is a quarter. Root 3 by root 3 is 3. 2 over 2 is 4. Quarter plus 3/4 is 4/4, which is 1. So the modulus of this is 1. So this is a length 1. It's not making the number bigger or smaller. It's multiplying it by itself. It's just rotating. So rotate, rotate, rotate. That is the cubic root. So that's the cubic root, and one of them, and the other one is there. So the cubic roots of 1 are there. And then we can see it there in terms of cos 2 pi over 3 and I sine 2 pi over 3. So that's the way they work. So they're the cubic roots of 1 plus 0i. Now, we'll now use de Moivre's theorem. De Moivre's theorem is this: cos n theta is cos squared, or, well, basically he said cos theta plus I sine theta to the power of n was cos n theta plus I sine n theta. So n could be any value, but let's just do it for 2 when n is 2. So cos 2 theta and sine 2 theta must be cos theta plus I sine squared. So use de Moivre's theorem to show this is that, cos 2 theta is this and sine 2 theta is that. Let's see what it means. De Moivre's theorem states that cos theta plus I sine theta squared is cos 2 theta plus I sine 2 theta. This is a real number. This is an imaginary number, a plus bi. That's a value in a calculator. That's I, value in a calculator. That's the real bit. That's the imaginary bit. Let's square that to each other. So it's the FOIL method. So first outside, inside, last. Cos, well, we have to do it, sorry, that's squaring it. So I better just write it out, get the two bits itself there. So we'll say cos theta plus I sine theta by cos theta plus I sine theta. So cos by cos by sine with an I, sine by cos with an I, and then sine by sine squared with I squareds. So if we work that out, we get, that's the multiplication. Cos squared is cos by cos. Cos by the I sine and the I sine by cos, we get two of them in the middle. And the sine by the sine, we get sine squared, but the I is squared too. I squared means a minus 1. So we end up then with cos squared plus I squared sine squared. The I squared is minus, so cos squared minus sine squared. And this is the 2i. Now what's important about this is real and this is imaginary. So that's the real bit and the imaginary bit. So when we expanded all of this out, we got a real bit and an imaginary bit. Now, and that's the same as this, a real bit and an imaginary bit. So this was the cos 2 and this was the cos without the number 2. So with the 2, this was the real and imaginary. So we're left with then, the real part is cos squared theta minus sine squared theta. That's the matching of the real. And for the I sine 2 theta, this was the I, we can leave the i's out, we get 2 cos theta sine theta, we get 2 sine theta cos theta. So that's how all those equations that they give us in the trigonometry section and they give in the formula, that's how these are all worked out. It's really pretty neat. And it's all done through de Moivre. So we've more or less finished complex numbers. Complex numbers, that's about it. And they say, well, how do we use them in other parts of the course? So this is just complex numbers being applied somewhere else. There's no new complex number material really going on here. But just how can they fit it into another question to link it to another part? Because as I say, there's no choice in the paper. They can pull a question and link it to anywhere. So we start with arithmetic and algebraic equations. You would have heard of BOMDAS, brackets, order, multiplication, division, addition, and subtraction, the order in which we do things. Whereas in the States, they talk about PEMDAS, parentheses instead of brackets. Please excuse my dear Aunt Sally. So here's a question. Simplify 3 plus I into all of this. How do you do that? And it's just an expression and we just take our time really. And we say, what is the order in which this is done? So within the brackets, we have an I squared and that's a power. So we'll solve that first. So the I squared becomes minus 1. So 3 by 2i plus I minus 1. So we still have the I outside. Inside the brackets, we still have 3 times 2i, that's multiplication, so we'll do that next. 3 by 2i is 6i. So we have 6i plus I minus 1, and inside, they're really the same. They're both imaginary numbers, so I think it's worth adding those two together. So 6i and I gives 7i. 7i minus 1, nothing we can do there. That's like apples and oranges. We can't subdivide them more. We have an I outside. So I multiplying in, now we can do that. I times 7i is 7i squared, and I times minus 1 is minus I. So this is okay, but the I squared now we need to solve because I squared is minus 1. So that's 3 minus 7 minus I. 3 and 7 are real numbers, so we can simplify that to minus 4, and minus 4 minus I, and we're done. So that's an arithmetic example that they could ask us to simplify. Complex numbers now using algebra. They said, this was the philosophical thing earlier. We said that if two numbers are the same, a plus bi and c plus di, they have to have the same. So if Brian and Joe have the same numbers of apples and oranges, they have to have the same number of apples as each other and the same number of oranges as each other. So b must equal d and a must equal c. So how does that come about? Well, here's a question that you mightn't expect at all in complex numbers. And you'd say, what is this about? Seen nothing like this before. S plus ti is 1 plus 3i squared. I've heard about i's. What's this s and t bit? You say, I don't know, haven't a clue, but I can do the multiplication. So let's pick up some marks. So 1 plus 3i by 1 plus 3i. 1 by 1 is 1. 1 by 3i is 3i. 3i by 1 is 3i. 3i by 3i is 9i squared, and it's plus. So that's 1 plus 6i. 9i squared, well, 9, that's a minus 1 really. So adding the real bits, I get minus 8 plus 6i. So in other words, at least I could do the right-hand side. I multiply it out, and I get minus 8 plus 6i. And it now says s plus ti is minus 8 plus 6i. Solve. And you look at it and you say, well, okay, but s is real, and that's imaginary. So if we were to compare reals with reals and say, this is the real bit, and this is the imaginary bit, we really have two equations. So s equals minus 8 is the real, and t equals 6 for the, or ti is 6i, is the imaginary. And you say, oh, I've solved it. Oh, that's all I wanted. S is minus 8 and t is 6. So that's all that was going on in that question. Here's another good exam question. Solve k into w plus w bar is 20, where w equals 2 plus 5i. And you say to yourself, this is unfamiliar. What's this bar thing? But that's really where they're only just letters in the alphabet. So once we know that w bar is the complex conjugate, then we'll try it. So w is equal to 2 plus 5i. W bar then will be 2 minus 5i. And let's see if we can do the question. So it says k into w plus w bar. Well, w is 2 plus 5i, w bar is 2 minus 5i. W plus w bar is 2 plus 5i plus 2 minus 5i, which is 4 plus 0i plus 4. And that's good news, because adding a complex number to its complex conjugate should really give us a real number. So effectively, k into w plus w bar is just k4. So k4 is 20. But 4 is just a multiplier. That's 4k is 20. And I think we know how to solve that. K is equal to 5. So that's all that was going on in that question too, even though it looked far more challenging, let's say, at the top. That's all it was. Here's a longer question, and they say, okay, x into 1 plus 3i plus y into 2 minus I plus 2 plus 3i equals 7 plus 4i. Well, it's certainly long anyway, and it's something that we've never seen before, but we could look at the real bits and the imaginary bits, because 7 is real, and the 2 would be real, that 2 would be real, and that 1 would be real. And we could look at the imaginary bits, and we could say that's imaginary. And let's just join up the real bits together. X by r would be just, x by 1, would be just x. So we do the real bits first. So you get x plus 2y plus 2 is 7. And the imaginary, you get 3xi minus yi plus 3i is 4i. That 2 we could probably take over to the other side or something like that. But let's see how we get on. On the real components, we get the x and the 2y and the 2 and the 7. So x plus 2y is 7. And if we took that 2 over to the other side, we get x plus 2y is 5. If we took this 3i over to the other side, we'd get 3xi minus yi is I. And in fact, I think we could get rid of all the i's. And we could say 3x minus y is 1. So effectively what we've done with all of this is we've taken this enormous line here and broken it down into 3x minus y is 1 and 2x plus 2y is 5. There are two simultaneous equations from a totally different part of your course, which you could then decide to solve for x and y's. Nothing to do with complex numbers, but it was just a way in to give you two equations, that's all. Now, nearly finished. We look at the roots of polynomials. In different parts of the course, we have these lovely graphs. They're nice quadratic graphs, and they come down nicely and they might cross the x-axis at various points. They might have a minimum point and go back up. There's other graphs that come down and they just skim the x-axis. They just touch it bang on the button there. And they might have two roots exactly that are twin. They might be symmetrical just at that point. So for example here, x squared minus 6x plus 9 has two roots, and they're both x equals 3. Because x minus 3 by x minus 3 gives us this here. So there's only got one root, well, two roots, but they're the same point. But this one here is stranger because it's got a quadratic, but it never actually hits the x-axis. So does it have roots at all? Well, with complex numbers, we can say that it can have imaginary roots. So I'm sure at some stage in all the time you're doing the junior certificate where you did the plus or minus b squared minus 4ac over 2a. No doubt at some stage this turned out to be a minus, even though it shouldn't have been. It was just a slip or something that we all do. But now we can look at the square root of a minus number and say, but sure, that's only I. Or the square root of minus 4 would be just the square root of 4 by the square root of minus 1, which would be 2i. So we can now get the solutions for things that have a minus. Now they may not be on the real number line, but at least they're complex roots. So find the root of the quadratic equation fz is z squared minus 6z plus 12. We do it exactly the same as we would for a quadratic. And so we say az squared plus bz plus c. And we say, what's the coefficient of the a? A is 1. What's the coefficient of the b? B is minus 6. What's the coefficient of the c? It's 12. And we have the formula. And we just go off and we do the sum then, and we work through the stuff. But unfortunately, we end up with 6 plus or minus 2 root minus 3. Root minus 3. Oh, okay. Because this number here turned out to be negative rather than positive. So it's no longer a real root, it's minus. But the square root of minus 3 is the square root of 3 by the square root of minus 1. And the square root of minus 1 is just I. So now we've got a root that said z is equal to 3 plus or minus root 3i. So this equation, rather than having no roots, has two complex roots. So once we've done it, that's the equation. We've got the answers and say that's one of the roots. We can say, show that it is a root. So everywhere there was a z, I'm going to put back in 3 plus root 3i. So 3 plus root 3i, I'm going to square it, minus 6 times it, plus 12. And I'm going to work that through, squaring it out, calculating it. What do I find? I find it's not. So just as I might have done, let's say x squared minus 2x plus 8, and I put in when x is 4, I got naught. Now I'm going to do this, and when z is equal to this, I get naught plus naught I. So that's how I can work out what a root of a complex equation is. If the two roots are this, the complex conjugate must be in there as well. So they're the two roots. Then the two factors must be this. So remember, in real numbers, we said if x equals 4, then x minus 4 equals 0 must be a factor. Well, if z equals this, z minus that must be a factor. So that's a factor, and that's a factor. So z minus 3 minus root 3i times z minus 3 plus root 3i must be factors. And if we multiply the two factors together, it's a lot of stuff. It's the first by the first, first by the second, first by the third, second by the first, second by the, all the way. What do we get? Z squared minus 6z plus 12, the actual function again. Just as if we multiplied x by minus 4 by x plus 2, we'd end up with the function again. So if we multiply by the factors, we get the function. Where the roots of a quadratic equation are known, the quadratic equation can be expressed as, now somewhere in the tables it says you can always get the expression from a quadratic by the z squared, the sum of the roots, and the product of the roots. So the two roots were 3 plus root 3i, 3 minus root 3i. So adding them, the sum gave me 6. Multiplying them together, the answer gave me 12. That's another way I could find that it's actually the right equation as well. So here's the last one. Given that Z1, so this is a cubic now. This is a cubic complex number equation, cubic polynomial in complex numbers. Z1 is 1 plus 3i, is a root of a cubic equation. There's the cubic equation there. You're asked to find the other two roots. Well, the good news is that if one of the roots is complex numbers, it's a complex number, there must be another one in there as well, and it must be its twin, it must be the complex conjugate. So if that's one of the roots, then the other root must be 1 minus 3i. So if they give you 1, they're actually giving you 2. So Z1, 1 plus 3i, and Z2, 1 minus 3i are roots. If they're roots, they're factors. You say Z1 equals 1 plus 3i, then Z1 minus 1 minus 3i must equal 0. So that's factor 1 and factor 2. Multiply the two factors together, a long-winded way, and you end up that the two factors are, you get that. So that's your quadratic. So now you know that z squared minus 2z plus 10 is actually another factor. So that's a factor, the two of them together is a factor. Another way you could have done that was to say the factors are the sum of the roots and the product of the roots. The sum of the roots were 1 plus 3i, 1 minus 3i, that's your 2. The product was your 10. So that's exactly the same as the previous page, where that's your other factor, either by multiplying them out or by doing this trick. So the last thing then is to look at this and say, this is the cubic one we want to find the root of. This is actually one of our factors. So how often does the quadratic go into the cubic? How often does z squared go into z cubed? Well, z squared into z cubed goes in z times. So z times z squared is z cubed. Z times 2z is minus 2z squared. Z times 10 is 10z. Now we're going to take this from this. So they cancel. This becomes a plus. So that becomes, and this becomes 2. So we're left with minus z squared plus 2z, taking the 10 down. How often does z squared go into minus z squared? Just 1. So minus z squared plus 2 minus 10. 0, 0, 0. So the three roots are the first one, you were given. The second one, the complex conjugate. And the third one, z minus 1 is a root. Z must equal 1 is the other. Sorry, is a factor. That must be the root. And that's the end of complex numbers. So fairly close on time. Thank you so much for your time. And we're going to take a well-deserved break. We're going to come back at 4 o'clock, and I hope you'll join me for the last topic. I know it's been a hugely long day taking 90-minute classes like this, but we thought we'd cover as much as possible and to give you a feeling on that. So we're going to finish with probability, and we're going to come back at Caraclog. So Gadishan, Slán. And I just left these three things up because I got a few questions there in relation to the last session. So I think I've got the names there. I've got Olivia and I've got Emily, and I think I have another question there as well. But basically, there was a question there about proof by induction, and similarly too for the differentiation from first principles. In situations where the differentiation from first principles are really just a learning off and a rote learning of the method, I haven't put those up yet as sessions in their own right, because it's really just a transcription from any of the maths textbooks that you would have. It's just, you know, can you differentiate from first principles, and you learn off the 4 or 5 that are there. So I haven't done that in either the proof or in the differentiations. One thing that I did do on the geometry is I did the constructions. So to show how you physically do the construction with the compass and a triangle and get the incircle and all that, incircle and lower circle and all that, they're all done, and they're on the site under the geometry section. So you'll find those, because, you know, that's actually a physical thing. But on those, I didn't reproduce those. There was a question there from Olivia. She asked about the algebraic long division, really, and it's just a process where I did it there with the cubic. But let's say that x equals minus 1 was a root, then x plus 1 equals 0 is a factor. And let's say the equation was, or the function was, x squared plus 2x plus 1 was the main one. How would you divide x plus 1 into that? Well, basically you say, how often does x go into x squared? And you say x goes into x squared x times. X by x is x squared. X by 1 is x. Then you take that, and that cancels, and you're left with just x plus 1. And you say x by, so you say, well, how often does it win? So you've done the first one, and you say, let's try 1. 1 times x is x. 1 times 1 is 1. So it looks like the other factor is x plus 1. So x plus 1 is the other factor. X equals minus 1. So that actually is a symmetrical curve there. It only crosses and touches it at the one spot, which is fine. But really the only difference between that and a cubic is that there's more stuff in the cubic. So it might be x cubed plus 3x squared plus 2x plus 1 here. And you might have a longer thing going into it, that's all. And it's just more tedious, but it's exactly the same approach. Emily asked a question about something like this, like maybe a cubic function, or maybe even more, that had various roots, and said you're told 2 of the roots at the x-axis, or y equals 0, and you're also told about a point there as well. So let's imagine that this is some ax cubed plus bx squared plus cx plus d. Let's imagine it's some cubic expression. Well, if there's a root at a, and let's say that's 1, 2, 3 away, well then when x equals minus 3, that's a root. Then we could say x plus 3 is a factor. So we could plug x plus 3 into this, and it would reduce it down to a quadratic. Similarly, if this was a factor, if x equals 3 was a factor, we could say x minus 3 is 0. And we could use that as a root. Or if we knew the 2 of them, we could say x plus 3 by x minus 3. I think we get x squared minus 9 or something. And we could divide that into the cubic. And then we would get down to some sort of nice equation, maybe with just an x in it. So let's say we had cx plus d equal to something. We wanted to solve it. We can find on the point on the y-axis, that when x is 0, then we would know this point here. So if x was 0 here, this point here is also 3. So if we put x is 0 into here, then we would find that that's equal to 3. So the D is 3. So that might help us find the C as well. So that's how you tease your way around that. They're the sort of questions that come up. So thank you for that.